Welcome students of Thakur Vidya Mandir High School and Junior College. Students, we are back with chapter 11 Magnetic Material Part 2. This ends up your chapter. In this we are going to study the concepts which I have mentioned earlier in part 1, that is the types of the magnetic properties and their applications. Let us move on with the first two concepts, that is permeability and permittivity. Magnetic permeability, which is nothing but the allowance or called as permittivity in electrostatics. It is the number of the magnetic lines of force passing through a given substance when it is kept in an external magnetic field. The number is the indicator of the behavior of the material in the magnetic field. Let us move on to the second concept, that is magnetic susceptibility. Now, susceptibility is denoted by capital H, which is not too strong if the magnetization M is induced in the magnetic material in the external magnetic field. Then the quantity, that is eta, is called as magnetic susceptibility. So it is observed when your H is not so strong in the magnetization M. It is a dimension less constant. The number of the atomic dipole moments of getting aligned in the direction of the applied magnetic field is directly proportional to the magnetic susceptibility. Therefore, it is large for the soft ion, where we could relate it as greater than 1000. Let us move on to the first property, that is diamagnetism. Diamagnetism was given by Lenz. Lenz's law actually states us the moment of the electron around the clockwise or the anti-clockwise directions. Here in the figure you could see in part A we are showing that it is for the current loop where the direction of the induced current is opposite to the direction of the loop current. Thus the net current is reduced, effectively reducing the magnetic dipole moment. Let us see the second figure. Now in this loop you could see that the direction of the induced current is same as that of the loop current, and this will find an increase in the current I, resulting in an increase in the magnetic dipole moment. Students, let us consider the diamagnetic substances in a uniform magnetic field, a few examples of which are copper, gold, bismuth, lead, silicon, glass, water, wood, plastic, etc. Now in the diagram you could see the electric field showing you the formation of the magnetic field around a particular substance. Now this is from the north to the south pole, and the capital P representing the magnetic induction. When I talk about the property, students, the first property, that if I place a diamagnetic material in an external field, the induced magnetic field ripples the magnetic lines of forces. When I place it in a non-uniform magnetic field, it moves from the stronger to the weaker part of the field. If a diamagnetic liquid is placed in a U-tube in an external magnetic field, the movement of the diamagnetic liquid will be towards the upper portion of the U-tube. The magnetic susceptibility of a diamagnetic material is most of the time negative. Let us move on to the second property, that is paramagnetism. The metals such as magnesium, lithium, molybdenum, tantalum, water and oxygen gas are examples of the paramagnetic materials. Go through the diagram. The paramagnetic substances, when they are placed in the external magnetic field, you could see that there are few lines which are clustering around towards the end of the substance which is kept in the magnetic field. Let's see the properties of paramagnetism. When paramagnetic material is placed in a non-uniform magnetic material, it tends to move from a weaker region to a stronger region. When the magnetic field is removed, these magnetic dipoles get themselves arranged in the random directions. If I talk about the net dipole moment, it is zero, which is in the absence of the magnetic field. The third property of the magnetism is ferromagnetism. Ferromagnetism is shown by the strong magnets, for example, iron, in which you cannot remove the magnetism property out. Now let us talk about the unmagnetized state. With the figure, it is very clear that in an unmagnetized state, the domain axes of the different domains are oriented randomly. When you move towards the right hand side, students, you could see the magnetized state where the black arrow is showing the magnetic induction and the arrows are oriented. Thus, in an external magnetic field, the domains align in the direction of the applied magnetic field. Let us understand the effect of the temperature on ferromagnetism. Ferromagnetism, we have seen that in the presence of the magnetic induction, it aligns in a particular direction. But as the temperature of the ferromagnetic material is increased, the domain structure starts distorting, and because of this, exchange of the coupling between the neighboring moment weakens. Thus, at a certain temperature, depending upon the material, the domain structure collapses totally and the material starts behaving like a paramagnetic material. It is given by a temperature which is Tc, called as Curie temperature. When I write down the formula, my magnetic susceptibility is equal to capital C divided by T minus Tc, that is the Curie temperature. When you see the diagram, students, it is very much evident that your magnetic susceptibility is along the y-axis and the temperature showing along the x-axis. The ferromagnetic curve is showing you a downward slope where the paramagnetic material is formed just because of the domain structure getting distorted. Let us move on to one more concept which is called as hysteresis. Hysteresis is nothing but the magnetic history of the sample. If I refer the hysteresis cyclic loop that is given in figure 11.11 on page 261 of the textbook, there you could be seeing that the curve is moving in a forward direction, which is showing you that on passing the current through the solenoid, the magnetic field is generated, which actually magnetizes the rod. The value of the magnetic susceptibility of the material of the rod, that is M, can be easily calculated by using the formula capital M is equal to magnetic susceptibility multiplied by H. Thereby, knowing the values of the H and the M, we can calculate the corresponding magnetic field. As the strength of the magnetic field increases, the increase is nonlinear. When you refer back to this figure on page 261, you would be seeing an upward curve rising towards the y-axis. Let us move on to the applications of magnetism. Now, magnetism basically is used for electromagnets as well as the formation of the permanent magnets. Soft iron, which is having a large permeability and a small amount of retaining magnetization, is used to make electromagnets. If I move on to permanent magnet students are prepared by using a hard ferromagnetic rod instead of a soft rod. So when the current is switched on, the magnetic field of the solenoid magnetizes the rod. The last application of magnetism is magnetic shielding. Students, in this, when a soft ferromagnetic material is kept in a uniform magnetic field, the large number of the magnetic lines crowd up inside the material, leaving a few inside. So if we have a closed structure of this material, say a spherical shell, as I have placed in this figure, is kept in a magnetic field where few lines of the force pass through the enclosed space. Most of the lines will be crowded into the iron shell. This particular effect is known as magnetic shielding. So, when I talk about the instrument which needs to be protected from the magnetic field is surrounded by a soft ferromagnetic substance, this technique is used basically in the spaceships. Thereby, we could say that some scientific experiments require the experiment to be protected from the magnetic field in laboratory also. Thereby, the high magnetic fields of magnets can be shielded by providing a case made of the soft ferromagnetic material. There are different types of shielding available in the electrical and acoustic shielding apart from the magnetic shielding. The electrical insulators function as the electric barriers or a shield and comes in a wide array of the materials. So the recording studios and the sounds are also insulated by using the acoustic materials. So these were the final applications of the magnetism. Let us move on to the assignment question, students. The question mentioned out here are: which property of the soft iron makes it useful for preparing the soft magnets? What happens to the ferromagnetic material when it is kept in an increased temperature above the Curie temperature? Why does the hysteresis loop represents a particular shielding area? Explain one application of the electromagnet. One application either could be a permanent, either could be an electromagnet or a magnetic shielding apparatus. Reference books are the textbooks. Please go through the links which are mentioned out here. Prepare your notes thoroughly with the neat label diagrams. Thank you, students.